heat of vaporization. Now this one, they're giving you joule per mole and joule per gram. But we'll do the joule per gram. So water is 2,257. But in order to keep it as calories, let's just do calories. So we'll take this number and we'll divide it by 4.184. $539.44. Heat of vaporization of water, 539.44 calories per gram. So those will be our basic ones. And it does look like water is also high on that list too, 22.57. But then there's iron, which is 6,000, so that the iron is more. Aluminum is 10,000. So metals are not only have a high boiling point, but they also have a high LV, right? That's their boiling point there. For iron, it's 3,134 Kelvin. So it boils at 2862. Well, that's a typical temperature of even a cold star. Cold star is 3,000 Kelvin. So no metal is going to sustain its solid or liquid form. It's going to turn into a gas, right? And the sun does have iron in there, small bits of iron, but it's in gas form. Because the core of the sun is 15 million Kelvin. So by that point, nothing is left in liquid form. It's all solid. It's all gas. Yeah, see, aluminum is 3,000 Kelvin too. Right? But brown dwarfs, which are colder stars, they're about 2,000 Kelvin, 1 to 2,000 Kelvin. So they might have some on their outer portion, they might have some liquid, I guess. You know? How about Jupiter? Is it all gas or could it have liquid? On the outer portion, mainly gas, but as you go in, the pressure gets high, the temperature gets high, right? And you might actually have some of the hydrogen in it turn into liquid form. And it actually does. It has a liquid metallic hydrogen in its interior. Okay, cool. Okay, so what kind of situations or problems are there that utilize this? Well, mainly since this has to do with changing temperature, it has to do with equilibrium, systems reaching equilibrium, right? So there is a whole host of calorimetry type problems you can do with this. They're called calorimetry. Or you don't necessarily have to do calorimetry problems. Other kinds of problems could be anything where something you're, let's say, dragging something, you're doing work on something, and friction is doing work on the system. When friction does work on the system, it shows up as heat in the system. You see? So you can have those kind of problems. So we could say problems involving specific heat and heat of fusion and heat of vaporization. Then we have calorimetry problems. And then we have problems that we can call it general situations where friction is doing work. Okay, so suppose I gave you something like this. Block of ice. So let's say there's a 2 kilogram block of ice, initial temperature is 0 Celsius, initial velocity is 0, and then final velocity, the initial height is 20 meters, and then the final velocity is 8 meters per second. Like I say, the final velocity when it hits the ground is 8 meters per second. So then I can say how much of the ice will melt by the time it hits the ground. How much of it melted. Given this scenario, how much of the ice melted by the time it hit the ground? By the time, or we say just before it hit the ground. Melted just before it hit the ground. Now, at first, it might look like there's not enough information given. What do you mean? How do I translate this problem to a temperature, right? Because this looks like a more typical physics 1 question, right? Just blocks and stuff like that. But what's the relationship? Okay, so now since I give you the height and I gave you the initial velocity, final velocity, what's happening here? Since I've given you the final velocity, I haven't asked you solve for the final velocity. I've given you the final velocity. So what we should do is try to find out if friction did work, air friction did work on this ice. Did it do work? In other words, if friction hadn't been present, if air friction hadn't been present, what would the velocity have been if you drop it from 20 meters? I think it would have been a lot more than 8 meters per second, right? So that fact that the velocity is 8 is already telling you secretly that, hey, friction has done work on this system. You see? So what's the equation? Work by friction equals changing kinetic energy plus changing potential energies. So this is the physics 1 work energy theorem, right? This is what we're doing in physics 1 now, right? So now we're using this as a physics 2 problem. So what's the change in kinetic energy? Half m v final squared minus half m v initial squared plus potential energy final minus potential energy initial. Right, so if friction was not present, then of course the final velocity would have been more, right? So in my case, V initial is 0, H final is 0, so then I have work of friction is going to equal half m V final squared minus mg H initial, right? Half times the mass of the block times V final squared minus the mass of the block times 9.8 times 20. Right? So you put the final kinetic energy minus the initial potential energy. So you're going to get 64 minus 40 times 9.8. Okay, friction will always do negative work, right? At least in most cases, will do negative work. So that work done by friction does what? Well, it goes into the atmosphere, dissipates as heat. It probably warms the air up, but more directly, it warms the ice, right? It does warm the air, but let's assume most of the heat goes into the ice. So then what's that going to do? It's going to heat up the ice. But in our case, since the ice is already at 0, it's not going to heat it up, it's going to immediately start melting it. Because you're already at the melting point, right? So that heat, 328, is equal to H, is equal to MLF. The mass of the ice times the heat of fusion of ice. So now that one will tell me how much mass of ice will melt. Okay? So then what's going to happen? 328 is equal to the mass of the ice. Heat of fusion of ice is what? Now what units should I do? Okay, the one that I gave you was heat of fusion was 79.22, right? Calories per gram. So now we need to be careful. I can't just take that number and plug it in there. I got to make sure the units work out. So if this is joules, this is kilogram. So what units should I do here? Joules per kilogram. Oh no, sorry. The mass is not kilogram. We're trying to find the mass of the ice melted, but you know what? We could leave this as this. Depending on the units of the LF, the answer will either come up in grams or kilogram, right? So what units can I do? Well, at least I need to change this to joule per gram, right? So then I can say 1 calorie is 4.184 joule, and then that'll be the other form. $331.46 joules per gram. Now, do I need to use kilogram? No, not really, because if I leave it like this, what's going to happen? Joule will cancel, this gram will go over there, and my answer will come out with these many grams of ice will melt, and it'll just be grams, not kilogram. I think in my case, I just need to leave it in gram, because it's not going to be a lot of the ice that has melted. It's going to be very small. So this number divided by this, okay, barely, not even a gram. So it sounds like that's a lot, right? Oh my gosh, friction did 328 joules. The number sounds a lot, but when you compare with the heat of fusion of water, it takes 331 joules just to melt 1 gram of ice. Oh, that means 300 something is not a lot at all. Just to melt 1 gram of ice. So, in other words, the joule is not really a large unit of energy. It's kind of proving that. Now, if you do kilojoules of work, 300 kilojoules of work, oh yeah, then you're going to melt 1 kilogram of ice. Now we're talking more significant, right? But 300 joules is not that much at all. So there's a whole host of problems that kind of resemble this, that are not calorimetry problems. They might be related to physics 1 cases. And the idea behind them is that once you find the work of friction, then that becomes the heat that goes into the system, and now you can do a thermodynamics problem, right? The other kinds of cases are calorimetry, where you're mixing some stuff together and then you're finding out what the final temperature of the system is. Have you done those ones in chemistry? Probably in chemistry you might not have done this type, you know, but you might have done the calorimetry. So let's say you take, for example, imagine you have a very insulated thermos, you know, styrofoam or something. So now let's say there is 200 grams of ice. Let's make it more. Let's say 500 grams of, it's 500 grams of water at 20 degrees Celsius. Then we put in there 2 kilograms of ice at -5 Celsius, right? So we put in the ice in there, and we also put in some steam. Then we put in 800 grams of steam at 105 Celsius. So we got a bunch of stuff that we're mixing together. Now, how do you put in the steam? I guess you boil something else, and then you go like this, and then the steam comes in. Right, so once the steam comes in, then you close the lid. Close lid. So let's assume no temperature escapes the system. What's going to be the combined temperature of all three of these mixtures, right? So the steam is going to start cooling, right? Because it's at 105. It's got to start cooling. Once it reaches 100, it's got to condense back to liquid, right? And then after it turns into all liquid, let's assume it does turn all into liquid, then it's got to cool back down. All in the same time, the water has to increase its temperature. The ice has to increase temperature, melt, right? And then once it melts, it turns into water, then it goes up, and then somewhere they meet in the middle of all this, right? So what's the expected temperature? Well, if all the steam melts and all the ice melts, probably the expected temperature is maybe greater than 20, less than 100, somewhere in there. But could it be different? Yeah, you might have, maybe if you have enough ice, you might have the final temperature less than 20. We don't know, right? So how do we set it up? Well, what you could do is assume, make a certain assumption, and whatever answer you get, then you can kind of interpret it. So let's assume T final is less than 20, but less than 100. So if we assume that T final is less than 20, but it's less than 100. So then we're going to assume all of the steam has turned into liquid and all of the ice is melted. So we're going to say H lost by steam is going to be the heat gained by the water and the heat gained by the ice, right? So how much heat is lost by the steam? I'm taking the absolute value of it, right? Absolute value of the heat lost by the steam. So the mass of the steam is 800 grams. Okay, how much heat is it losing while cooling down to 100? What's the word specific heat is hard to say. Specific. Your tongue is like, it's like a tongue twister. Specific. Specific, 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 specific. Say it 10 times and then your tongue will twist. So specific heat of steam is 0.5, right? 0.5. So I'm going to say 0.5 calories per gram Celsius. Then it's got 5 Celsius to go to reach 100. 5 Celsius. The reason I'm writing the units so that you can see how it works out. Celsius, Celsius cancel, gram, gram cancel, right? And then that's 0.5, that's ends up in units of small calories. Then how much heat will it lose in the condensing state? Then you take the mass of the steam, right? Gram multiplied by the heat of vaporization, which was what? 539 point something? What was it? You have it? That's calories per gram. This one, by the way, I don't have to convert to joules. I can keep them in calories. For this one, you don't need change in temperature because this is just condensing, turning back to liquid. Okay? So then the gram cancel. Plus, how much heat is losing once it turns into liquid? Now it's going to go down to some final temperature, TF, right? So then you're going to have 800 gram times 1 calorie per gram Celsius, because remember when it turns into liquid water, its specific heat is 1. And then what's the change in temperature? 100 minus TF, not TF minus 100, right? Because then TF minus 100 is going to be negative. It's going to make it look like it lost, because we're doing the absolute value of all the heat lost by it, so it should be positive. So you should write it as 100 minus TF. Okay, now that's equal to, now put the heat gained by all the other stuff. But the water is easy. It's just going to be 500 times 1 times TF minus 20, because the water is not changing phase or anything. All it's doing is increasing its temperature. Now I need to account for the ice. So the ice has to 2 kilograms, so that's 2,000 grams. I'm going to change it to gram, 2,000 grams. So what's the specific heat of ice now? Well, that's also 0.5. Happens to be about the same as steam, right? So then it's 0.5 times 5 degrees. Now I'm not writing the units anymore, so you see how it works out. So 5 degrees, why? Because it's 5 degrees away from reaching its melting point, okay? Then after reaching that, you have to melt it all. So 2,000 times the 79, right? 79.22. Plus, after melting, you got to raise the temperature of that to 2,000 times 1 times what? TF minus what? So now the change in temperature. So now you got to melt it, and you got to raise it to a final temperature TF, but its initial temperature is what? When you melted it, what was its original temperature? What's the melting point of ice? 0. Okay? So TF minus 0, which is just TF, right? So are you visualizing everything that's happening? You have to sort of see it in your head, like, oh, okay, you got the water, you're putting the ice in there. Ice is heating, then melting, then warming. Right? Heating, melting, warming. The water is just warming, and then the steam is cooling, condensing, and cooling. You see? So now let's set this all. 800 times 0.5, that's 400 times 5 is what? 2,000. Plus 800 times 5, 39.44, plus 800 times 100 minus TF is equal to 500 TF minus 20, plus half of 2,000 is 1,000 times 5 is 5,000, plus 2,000 times 79.22, plus 2,000 TF. You want to just put that in solver, or you can rearrange it yourself if you like. Rearrange everything. I think this one I would probably just rearrange, multiply the 800. So this plus 8, this is going to be 8,000, right? So 2,000. Minus 800 TF, 500 TF, TF minus, it's gonna be 10,000
The
plus 5,000
amount of energy for icing out, right?
plus 2,000 plus 2,000. Yeah. So this number and this number and this number I can combine and then I can take it over there, right? So plus 5,000. Then I can get 288,112. This one was, so I got rid of all of that. So then I'm left with 2,000 plus 500. 2,500 plus 800. 3,300 TF. Okay, here comes the moment of truth. That divided by that. Ooh, let's see. Oh, okay, it worked. 87.31. Yes, it worked. What would have happened if the answer had come out something weird, like 17.31? 17.31 means, okay, so that means the final temperature is actually below the water, right? So then would I have to redo everything, or could I still accept that answer? Because then if you put 17, it means when you put 17 here, that means the water actually cools, you know? I think the answer is you can still accept it. You don't have to redo it. No matter what the answer here comes out, it's acceptable, even if it comes less than 20, because it just means that the water cooled, the heat, instead of gaining heat, the water cooled, but the ice is still gaining heat. The only ones you can't accept is if you get an answer here equal to 100 or greater than 100. Or if you get an answer less than 0, you know.
Yeah.
Oh, okay, then you say something went wrong. That means there's so much ice. Because what if I had 200 kilograms of ice, you know? So then you might get an answer that's less than 0 and you say, oh, okay, then I have to redo it, you know? So anything less than 0, greater than 100, you might have to redo it and solve it. But anything between 0 and 100 should work.
I think your left side is wrong.
Yeah?
The 44.
So you don't water.
Did you add the 800?
I think I did, or maybe I didn't. I did, I added this guy to this one to this one.
What did that be? Because I got 513,000 something.
Which is 2,000 plus no, 441,000
Did you multiply 800 times?
times 100. Isn't that 8,000?
No, 80 times that. On top. The 800 times 5 cal.
Times a half. That's 400. Times 5 is 2,000.
800 times 100 is 80.
Oh, it's 0.5. Oh, that's
800 times 0.5 is 400. 400 times 5 is 2,000.
Well, 800 times 100